floor to Lawrence and continue.
All right, thank you very much for the invitation to speak, and thank you all for being here. So I am going to be talking today about some joint work with Lee Kennard, who's also at Syracuse University. And I'm talking about positive intermediate Ricci curvature with torus actions. Okay, so throughout the talk, I'm talking about Riemannian manifold. So M is going to be an n-dimensional Riemannian manifold. I will often not write the N or the G in this notation. And we are talking about symmetry rank, which is the rank of the isometry group of the Riemannian manifold. So that is the maximal dimension of a torus that can act isometrically and effectively on your manifold. So a foundational result in studying group actions on positively curved manifolds is the maximal symmetry rank theorem due to Grove and Searle, which says if I have a closed connected manifold with positive sectional curvature, then the symmetry rank is bounded above by roughly half the dimension. And in the case of equality, we have that the manifold is diffeomorphic to a sphere or one of these quotients of spheres. Right, and you can realize an action with maximal symmetry rank by just looking at the action of ON plus 1 on Rn plus 1 and applying it to the unit sphere in that Euclidean space. Okay, so to keep things simple throughout the talk, I'm going to consider only closed manifolds that are simply connected. Okay, and this result is foundational in that it serves as sort of the baseline for studying large isometry groups on positively curved manifolds. So there have been several generalizations in various directions of the maximal symmetry rank theorem. So I'll just give you a quick overview of them. So for considering non-negative curvature, we have work of Gallus, Garcia, and Searle, and Escher and Searle, and recently Dong, Escher, and Searle. So there's conjecture on how this should be generalized, and this has been established in low dimensions and under other assumptions moves on to higher dimensions. Considering a manifold that has positive sectional curvature just at a point, all the planes at one point are positively curved. Wilking generalized the symmetry rank upper bound, and Gallus Garcia in dimension 4 and 5 show that you have the same rigidity as the maximal symmetry rank theorem. For something called positive weighted sectional curvature, Kennard and Wiley considered the maximal symmetry rank theorem and showed that it generalizes similarly, except the diffeomorphism rigidity is a homeomorphism rigidity. And positive weighted sectional curvature you can think of as a generalization of positivity of the Bakker-Yemery-Ricci tensor. Not a generalization, but a strengthening, I should say. And if you replace the torus symmetry with a discrete abelian symmetry, then there's work by Feng and Rong and Kennard, Samani, and Searle. All right. Now, the generalization I want to consider is to positive intermediate Ricci curvature. So I need to tell you what that is. And throughout the talk, K is a parameter between 1 and n-1, one less than the dimension of the manifold. And so we say that a manifold has positive kth intermediate Ricci curvature. The following sum of sectional curvatures is positive. Okay, notice that in this sum, x is going to be in each of the summands, and the y's vary. So notice that if I say that Ricci 1 is positive, that means there's only one summand in this condition. It just means that sectional curvature is positive. If Ricci n-1 is positive, that means that we have positive Ricci curvature. The trace of the curvature operator is positive. And this interpolates between the two conditions. Because if I have positive Ricci 1, it implies that Ricci 2 is positive, and that implies Ricci 3 is positive all the way down to positive Ricci curvature. So the idea is that we have several obstructions to positive sectional curvature. You want to see how far down they can go in this ladder, this hierarchy. And you have lots of examples of positive Ricci curvature. So you want to see how far up this ladder you can climb for those various examples. So first, let me give you an overview of some examples that we have. Okay, a really easy source of examples is Riemannian products. So for example, if I take a product of spheres SM and SL, then that's going to have Ricci K positive for K equal to the maximum of the 2 dimensions plus 1. So it's easy to see if you take a vector in the SM factor, you can fill out the SL factor with an orthonormal basis. And the sectional curvature of this vector with all of these vectors is going to be 0. And so it's only whenever you throw in an L+1 vector in the first factor that you get your first positive sectional curvature. And you can do the opposite with SL. So this has Ricci K positive for some value K strictly greater than the dimension of the manifold. And Reiser and Wraith recently showed that this persists through connected sums up to some caveats. So you have to be in large enough dimension, and when M and L are equal to each other, you don't have quite the same value of K that persists. Okay, and also they showed recently, if you take a look at a fiber bundle where the base has positive intermediate Ricci curvature, the fiber has positive intermediate Ricci curvature, then the total space, if the structure group is compact, will also admit positive intermediate Ricci curvature. It'll have the same value of K that the trivial bundle would have. And this is especially useful for looking at exotic spheres. That shows that a lot of exotic spheres that were known to admit positive Ricci curvature now have a stronger condition that they satisfy, some positive intermediate Ricci curvature. All right. Another source of examples is symmetric spaces, and the minimum K for which each of these has positive Ricci K has been determined. And for an overview of that, there's 2 recent papers, one in which they study totally geodesic submanifolds of symmetric spaces. And in this paper that I co-authored with Miguel Dominguez-Vasquez and David Gonzalez-Savado, we show that using this information, we can get lots more examples by looking at something called fat homogeneous bundles over these symmetric spaces. So we can lift this curvature condition in those cases. And this is generalizing work of Wallach. All right. But the goal in this talk is to talk about how to generalize the maximal symmetry rank theorem to positive Ricci 2. We're taking the first step down from positive sectional curvature. Okay. And first of all, one thing to note is that the symmetry rank bound that we had in positive sectional curvature carries over to positive Ricci 2. That's due to the isotropy rank lemma that I'm going to cover in a second. And what Lee and I have managed to do is to show that if Ricci 2 is positive and you have maximal symmetry rank, so you have a maximal torus action on your manifold, then except for in dimensions, maybe in dimensions 4 and 6, or definitely in 6, but except for dimensions 4 and 6, we show that the maximal symmetry rank rigidity carries over up to diffeomorphism for spheres and homeomorphism for complex projection spaces. So that's a result that I want to outline here. And so let me tell you about some tools that we need. The first tool is the isotropy rank lemma, which is ubiquitous in positive sectional curvature. And it says that if I have an even dimensional positively curved manifold and I have a circle action, then that circle action has to have a fixed point set. And in odd dimensions, if I have a torus action, then there's going to be a circle subgroup whose fixed point set is non-empty in the manifold. Right? So in particular, this can be generalized, as I've done, by studying the killing fields that these torus actions are going to induce on your manifold. And if I have Ricci K positive, and I have a K+1 torus acting, then there's going to be a circle subgroup that's going to have a non-empty fixed point set. Right? So this is done by taking a look at the killing fields that they generate. If they were linearly independent everywhere on this closed manifold, then you could show that there's going to be a point in which Ricci K is going to necessarily have we're going to have a non-positive Ricci K. Right? But more importantly for this talk is that for Ricci 2, if I have maximal symmetry rank and the dimension's not 6, then there's going to be a circle that has a codimension 2 fixed point set. Okay, so I'll talk about dimension 6 in a little bit. This actually is not true in dimension 6 in general, but getting this codimension 2 submanifold that's fixed by a circle is key in conjunction with the next tool that we have. So the next tool is the connectedness lemma, which is Wilking's result from positive sectional curvature. And it says if you have a group acting and it fixes a submanifold in, codimension D pointwise, then the inclusion is highly connected. It's connected by this much. For those that don't know, when you say that an inclusion is connected, it means that these relative homotopy groups are equal to 0. So if you take a look at the long exact sequence of a pair for homotopy groups, this gives you information on the homotopy groups of the manifold and the submanifold and relates them. And so you can get information about the homology and the cohomology of the two manifolds as well. Okay, and the idea for establishing this is to essentially take a look at the curves that start and end in your submanifold N, and you can do a Morse theory argument to show that N is highly connected in the space of curves that start in N, and that tells you that N is highly connected in the manifold as well. So curvature comes into play in estimating the index of the critical points, the critical curves in the space of curves. All right, so in previous work, I showed that if you have positive intermediate Ricci curvature, then this carries over, but it gets worse. The connectedness is going to be less as K grows, because as K grows, you get a weaker and weaker condition, so you expect your conclusion to get worse and worse. All right, and the key difference is that in Wilking's argument, he uses a Cheeger deformation and uses the fact that positive curvature persists through a Cheeger deformation. Cheeger deformations are a way of taking a manifold with a group action and shrinking all the orbits systematically, and it preserves positive sectional curvature. It may not preserve positive intermediate Ricci curvature because you're allowed to have negatively curved planes. As you Cheeger deform, those negatively curved planes could blow up. All right, so the idea is instead to take a look at Jacobi fields along geodesics and use a comparison result by Guijarro and Wilhelm for intermediate Ricci curvatures that builds off of Wilking's transverse Jacobi field equation. But sparing those details, let me tell you what we get in the context of this problem. So I have a manifold with Ricci 2 positive. I know a bunch of them are going to have circles that fix a codimension 2 submanifold. So that means that this codimension 2 submanifold is going to be N-3 connected in M. Right? And furthermore, if you look in dimensions at least 8, you can show that the Euler characteristic of your manifold is going to be positive. And that's going to be helpful when we're looking at the even dimensional case in a little bit. Okay, essentially the connectedness of this inclusion allows you to push around zeros in the cohomology of your manifold M using connectedness along with Poincare duality. Okay, so in summary, what we've gotten from the isotropic rank lemma and the connectedness lemma is if you have Ricci 2 positive and you have maximal symmetry rank, if the dimension isn't 6, you're going to have a circle that fixes a codimension 2 submanifold. And we know how connected the inclusion is going to be for that submanifold. So in previous work, I showed, and this is a really easy consequence, that in odd dimensions, your manifold is going to be diffeomorphic to a sphere. Really, I show that it's a cohomology sphere that's simply connected, so it's going to be a homotopy sphere. And then I use Montgomery and Yang's result that if you have a homotopy sphere with a codimension 2 fixed point set of a circle, then the manifold actually is diffeomorphic to a sphere. All right, but in even dimension, yes. Well, isn't that using concavity of the distance function? Yeah, and that's, thank you for asking. Yeah, that's something I haven't mentioned yet. We're not working with positive curvature or non-negative curvature anymore, so we don't have concavity of distance functions anymore. That doesn't carry down into quotient spaces, orbit spaces. Right, so we don't have Alexandrov geometry at our disposal. Thank you. Now, if I want to attack even dimensions, it's really helpful that in dimensions 8 or more, we're going to have positive Euler characteristic. And so in particular, the manifold has a fixed point set for the entire torus action. So in particular, the submanifold N will also have positive Euler characteristic, and it will have a fixed point set for the its induced torus action. So the base case for our induction argument that we want to do is to take a look at dimension 6. And if I have a fixed point set in dimension 6 for a maximal symmetry rank action, then this manifold has to be diffeomorphic to a sphere or a complex projective space. Okay. The way to do that is to take a look at the fixed point set of the torus action. The T3 action is going to act diagonally on the tangent space. So you take each of the circles in the T3 that act on each of the complex coordinates, components of the tangent space. You look at the components of the fixed point sets of each of those circles, and you take a look at their Euler characteristics. You can do an inclusion-exclusion principle type of argument on the Euler characteristic of those fixed point sets of circles, and you can get information about the second Betti number of your manifold. Okay, so in particular, you show that the second Betti number is 0 or 1. Once you do that, then we have all of this connectedness. We can show that it's has the cohomology of a sphere or a complex projective space. And then we can use Montgomery-Yang in the case of the sphere, and we can use a result by Feng and Rong in the case of the complex projective space to show that we get homeomorphism and then diffeomorphism by classification of 6 manifolds. Right? So using that as our base case, we can then identify what N is. If M is 8-dimensional, N will be 6-dimensional. We know what it has to be. Then the connectedness of that inclusion will tell us that M has to have the cohomology of a sphere or a complex projective space. And we induct from there. Okay. So the homeomorphism classification that we're getting there is really just taking a topological result off the shelf from Feng and Rong. They established that if you have a cohomology complex projective space and you have a codimension 2 fixed point set of a circle that is n-3 connected in your manifold, then if that codimension 2 complex projective space is homeomorphic to a complex projective space, you get a homeomorphism to the ambient space. And I'm not sure how to or if anyone can beef that up to a diffeomorphism. How would you? That's essentially encased in Montgomery and Yang's result, where they construct a diffeomorphism from essentially Smale's work on the Poincare conjecture. No curvature assumptions for Montgomery and Yang. It's purely you have a homotopy sphere, you have a circle action whose fixed point set is codimension 2, and they show that the homotopy sphere is in fact diffeomorphic to a sphere. Okay, so this is a straight up generalization of maximal symmetry rank theorem. But the interesting cases are the cases that are left over, in my opinion. So dimension 6, what do we have? In dimension 6, S3 cross S3, product of 2 3 spheres, actually emits Ricci 2 positive. And we have T3 symmetry. So I have 2 Hopf actions on the left-hand side, component-wise, and I have a diagonal Hopf action on the right-hand side. So I'm thinking of each of those S3 factors as being unit quaternions. And the circles are just complex circles. So some things to note about this action is that it has no fixed points. All the non-trivial isotropic groups are circles. The singular orbits are diffeomorphic to tori. And the orbit space is homeomorphic to a 3-sphere. And what we managed to show is that if you have, in general, a manifold, a 6-manifold Ricci 2 positive, and you have T3 symmetry like we have here, if it has no fixed points, which is the remaining case in dimension 6, then 2 through 4 hold. What's missing is any sort of control on how many singular orbits you can have. In positive curvature or non-negative curvature, we could use Alexandrov geometry to control how many singular orbits there are. Here, we don't have any sort of tool, right? And for dimension 4, Orlick and Raymond have a classification of simply connected T2 manifolds. They're going to be connected sums of spheres, complex projective spaces, and S2 cross S2. And from the connectedness lemma, if a manifold has Ricci 2 positive and a circle fixes a two-dimensional submanifold, that two-dimensional submanifold has to be connected. Its conclusion into the ambient manifold is one connected. So as a consequence of that, when I take a look at, not as a consequence of that, sorry, when I take a look at Orlick and Raymond's classification, the T2 actions on S2 cross S2 and CP2 connect sum minus CP2, they both have to have a circle that fixes two disjoint surfaces in the manifold. So in particular, when you take a connected sum with each of these, because it's a classification of the equivariant diffeomorphism, any connected sum that has those as the summands cannot admit Ricci 2 positive with the T2 action. So ruling all of those out, what we're left with are the manifolds S4, CP2, and a connect sum of CP2s, all with the same orientation. I should point out that we don't know if these connect sums admit positive Ricci 2, a metric of positive Ricci 2. That's still an open question. Okay, so in summary, what we have is the following. So if the dimension is not 4 or 6, then we get the same spaces that show up in positive sectional curvature. When the dimension is 6, you might be able to have 0 Euler characteristic, for example, S3 cross S3. And in dimension 4, we might be able to have a connect sum of complex projective spaces. And I've been dealing completely with simply connected manifolds, so I just want to point out that we did consider the non-simply connected case. You either get homotopy equivalents to real projective space or a Lin space, or in dimension 6, we need more examples or we need more restrictions. But if in dimension 6 your universal cover is S3 plus S3, this is what we end up with. Okay, and I just want to end with advertising the fact that I keep a list on my webpage of publications that deal with not positive, but just intermediate Ricci curvature, because lots of different authors have been calling it lots of different things, and building this list, I actually took a lot of work because I keep discovering new names for this curvature condition. So I encourage you to check that out, and you can find our preprint on there and the other, a lot of the other stuff that I talked about today. Thank you.
Are there any questions?
Hi, thank you for your talk. Can you go back to the result where you generalized the Berger and Sukara, where you have Ricci K positive and TK plus 1 acts?
Yeah.
Okay, so I was curious, you have another result where you have Ricci 2 positive and T3 acting, but you assume the existence of a fixed point.
Yes.
So can I ask, why do you need to assume the existence of a fixed point?
That's an excellent question. The example of S3 plus S3, the torus action doesn't have a fixed point, and all isotropy groups are circles, right? And their fixed point sets are going to be two-dimensional tori. In this case, when we have a fixed point set of the whole torus, you can show that circles will have fixed point sets that are four-dimensional. So we get to use the higher connectedness of submanifolds in order to establish this result. What else do I want to say? Yeah, that's in essence what is helpful about assuming that you have a fixed point set of the torus action.
Okay, and then can I ask another question? Do you think, or what do you know about Ricci 3 positive and whether all this is going to work in that case?
Yeah, I decided not to put that in the slides, but we do consider Ricci 3 positive and Ricci 4 positive in either odd or even dimensions. I forget which right now. But in both of those cases, you have the same upper bound on symmetry rank as positive sectional curvature. And we establish rigidity, but we have to assume a lot more about the topology. So we have to assume that, for instance, that if we're doing Ricci 3 positive, we assume to get the sphere case that the manifold is 2 connected, which is a pretty big assumption. And in the complex projective space case, we assume that it has the appropriate cohomology up to a certain degree so that we can use the connectedness limit to then push that further and get the cohomology of the entire complex projective space.
Okay, thank you.
Thanks for your nice talk. So I will start with the case of dimension 4. So in the case of dimension 4, you have the Ricci 2 positive. Do you believe that you can replace Ricci 2 positive by some assumption like scalar curvature positive and co-curvature positive?
I can't say that I necessarily have an intuition for cooking up new metrics necessarily. The only other metric that I know of that is not listed on this slide in dimension 4 is the metric from S3 cross S3, which comes about from a Cheeger deformation. That if you mod out by the 2 circle actions on the left-hand side, you can get a Ricci 2 positive metric on S2 cross S2. And it doesn't fit into this because under that metric, there's only a circle symmetry. So the only examples I have so far come from essentially quotients. So in terms of coming up with examples through some other means, I don't necessarily have an intuition yet. I'm thinking about it.